Physics is not always a calm search for truth. Scientists often challenge each other's ideas, especially when the stakes are high. And few physicists were more direct than Richard Feynman. Feynman was a Nobel Prize-winning physicist, known for his sharp criticism and honest opinions. He believed that scientific ideas should always be tested with real experiments, not just impressive mathematics. In the 1980s, a new theory started attracting attention across the physics world. It claimed that all the forces of nature could eventually be explained by a single framework. For many physicists, it looked like a possible path toward a theory of everything. But Feynman was skeptical. He argued that the theory was becoming too abstract and too difficult to test in the real world. To him, a beautiful equation was not enough if there was no experimental proof behind it. The theory was string theory. It proposed that the universe is not built from tiny particles alone, but from incredibly small vibrating strings of energy. Different vibrations could create different particles, almost like musical notes producing different sounds. One of the young physicists defending this idea was Michio Kaku. He believed string theory could eventually explain some of the deepest mysteries in physics, including gravity and the structure of the universe itself. The disagreement between Feynman and supporters of string theory became one of the most famous debates in modern physics. It raised a major question that still exists today. Should physics only focus on ideas that can be tested right now, or should scientists also explore theories that may take decades to prove?
One of the most interesting things about the debate over string theory is this. Richard Feynman indirectly helped create some of the ideas that later supported it. Not because he believed in string theory. In fact, he criticized it many times. But the mathematical tools he developed changed how physicists think about the quantum world. Back in the 1940s, physicists were struggling with quantum electrodynamics, or QED. The calculations were incredibly difficult. Even simple particle interactions could produce pages of complicated equations that were almost impossible to visualize. Feynman came up with a smarter way to represent these interactions. He introduced what we now call Feynman diagrams. These diagrams turned complicated equations into simple visual pictures. Straight lines represented matter particles like electrons. Wavy lines represented force particles, such as photons. And when the lines met, it showed particles exchanging energy. The diagrams looked simple, but they were extremely powerful. They helped physicists calculate particle interactions much more efficiently and changed modern physics forever. At that time, physicists believed elementary particles were point-like. In other words, particles such as electrons had no size or internal structure. They were treated as tiny zero-dimensional points moving through space and time. This idea worked well for several forces of nature, but there was a major problem when scientists tried to include gravity in quantum physics. The equations started producing infinities that made no physical sense. At extremely small distances, the mathematics became unstable and broke down completely. Gravity refused to fit neatly into the existing quantum framework. Then a new idea appeared. What if particles were not tiny points at all? What if they were incredibly small vibrating strings? According to this idea, different vibrations of these strings could create different particles, similar to how different musical notes come from vibrating guitar strings. Surprisingly, replacing point particles with strings helped smooth out some of the dangerous infinities in the equations. The mathematics became more manageable, especially in attempts to describe quantum gravity. Feynman never set out to create string theory, but his way of visualizing particle interactions helped physicists think more geometrically about the quantum world. And from those ideas, string theory eventually emerged as a completely new way of looking at reality.
By the late 20th century, physics had reached a strange and important turning point. Scientists had already achieved some of the greatest breakthroughs in history.
Einstein had completely reshaped our understanding of gravity, space, and time. Quantum mechanics revealed a strange microscopic world where particles behave unpredictably. And physicists like Feynman developed powerful tools to understand that quantum world more clearly. But despite all this success, one major problem still remained unsolved. Modern physics was built on two extremely successful theories. Quantum mechanics explains the world of atoms, particles, and uncertainty. General relativity explains gravity, stars, galaxies, and the structure of the universe at large scales. Individually, both theories worked extremely well. Experiments confirmed their predictions with remarkable accuracy again and again. The problem appeared when scientists tried to combine them into a single framework. That is when the mathematics began to break down. The issue became even more serious when studying black holes. According to Einstein's equations, a collapsing star can form a singularity, a point where gravity and density become infinitely large. But in quantum physics, infinities are a warning sign. They usually mean something is missing or incomplete in the theory.
When physicists tried to apply quantum mechanics to gravity near a black hole singularity, the equations produced impossible results. Infinite energy, infinite curvature, infinite probabilities. It became clear that modern physics was missing a deeper framework. Because of this, scientists began searching for a theory that could unite quantum mechanics and gravity into one system. Even Einstein himself spent years searching for this unified theory, but he was never successful. By the 1980s, this search had become one of the biggest goals in theoretical physics. At the same time, the standard model of particle physics was achieving great success. It explained electromagnetic and nuclear forces with extreme precision. But there was still a major gap. Gravity was not included. So even though physics looked complete from the outside, many scientists knew something fundamental was missing underneath. The existing theories could explain a lot, but they still failed at the deepest questions about black holes, space-time, and quantum gravity. And whenever science reaches a deep crisis like this, new ideas begin to appear. That was the moment when string theory started to gain serious attention in the physics world.
Then came Michio Kaku. He entered physics at a time when the field was already under pressure. Many scientists were becoming more careful and cautious about bold new theories. But Kaku stood out because he was willing to explore large, unconventional ideas. He believed the crisis in physics was not a failure, but a sign that something deeper might be waiting to be discovered. That is where string theory enters the picture. String theory proposes a very surprising idea about reality. What we normally call particles, electrons, quarks, neutrinos, and even the hypothetical graviton, may not be tiny point-like objects. Instead, they could be different vibrations of extremely small strings. In this view, the basic building blocks of nature are not separate particles with different identities. They are all the same fundamental object, just vibrating in different ways. To make this idea easier to understand, Kaku often used the language of music. He would describe the universe not as a machine made of parts, but as an instrument. Just like a violin string can produce different notes depending on how it vibrates, tiny cosmic strings could produce different particles through different vibrations. From this perspective, matter is not made of solid stuff. It is made of patterns of vibration.
Kaku expanded this idea into a broader vision of the universe. He suggested that physics might one day reveal a deeper mathematical structure behind reality, something he sometimes called a cosmic code. Not a religious idea, but a final set of physical laws that everything in the universe follows. In this view, stars, atoms, chemistry, and even life itself are all different expressions of the same underlying vibrations. Unlike many theoretical physicists of his time, Kaku also became known for communicating these ideas to the public. He transformed complex mathematics into stories and images that people could easily imagine. To supporters, string theory represented a bold step toward unifying all of physics into one framework. To critics, it raised serious concerns because it was extremely difficult to test experimentally. And that was the main issue. String theory was mathematically elegant and powerful in theory. It naturally included gravity and even predicted the existence of the graviton. But there was still a major problem. At the time, no experiment could confirm whether these tiny strings actually existed in nature. So the theory remained both exciting and uncertain, a powerful idea waiting for experimental proof.
The disagreement between Richard Feynman and Michio Kaku was not just about equations or advanced mathematics. At its core, it was a philosophical debate about what physics should actually be. On one side stood Feynman, representing experimental realism. On the other side were physicists exploring highly mathematical ideas, like string theory. Feynman believed that a scientific theory only has value if it can be tested in the real world. For him, experiments were the final judge of truth. A theory should make predictions that can be measured, observed, and potentially proven wrong. Without that connection to experiment, even beautiful mathematics could slowly drift away from science and become speculation. This is where string theory created tension. String theory operates at an incredibly tiny scale known as the Planck length. This scale is so small that no current technology can directly observe it. Even the world's most powerful particle accelerators are nowhere near capable of probing such distances. At that extreme scale, physicists believe ordinary spacetime itself may stop behaving normally. The familiar concepts of distance and geometry could begin to lose meaning. For critics like Feynman, this created a major problem. If scientists cannot experimentally access these ideas, how can they know whether the theory truly describes reality?
The criticism of string theory became very serious. Many physicists argued that if a theory cannot be tested or falsified by experiment, then it moves outside the traditional boundaries of science. Critics worried that string theory could become mathematically consistent while remaining physically untestable. And a theory that can explain every possible outcome may eventually lose predictive power altogether. From this perspective, mathematics alone is not enough to confirm reality. Michio Kaku responded to these criticisms differently. He did not reject the importance of experiments. Instead, he emphasized the internal consistency and elegance of the mathematics itself. To Kaku and many supporters of string theory, the equations seemed too structured and interconnected to be accidental. They believed this mathematical beauty might point toward deeper laws of nature hidden beneath observable reality. In this view, mathematics is not just a tool used by physics. It may actually be the language the universe itself is built from. So in the end, the debate was never only about string theory. It was really about the definition of scientific truth. Should physics only accept ideas that can be experimentally tested right now? Or can mathematical consistency also guide scientists toward discoveries long before technology catches up? That question still remains one of the biggest unresolved tensions in modern theoretical physics. Early string theory was exciting, but it also had a serious problem. It was not a single, fully unified framework. Instead, it existed as several different mathematical formulations. Each version explained certain aspects of strings and their interactions, but none of them completely unified the entire picture. To many physicists, the theory looked powerful but unfinished, like a beautiful building with missing structural connections. Because of this, researchers began searching for a more rigorous mathematical framework. Their goal was not to replace string theory, but to rewrite it in a more organized and self-consistent way.
They wanted a single mathematical language capable of describing how strings move and interact. This effort eventually led to something called string field theory. In this approach, strings were treated more like fields in conventional quantum field theory. Instead of using many disconnected descriptions, physicists tried to encode the entire behavior of strings into one unified mathematical structure. Michio Kaku and his collaborators helped develop this formulation further. They expressed string interactions through a compact field theoretic equation capable of describing both the motion and interaction of strings within one system. For the first time, string theory began to look more mathematically complete and internally organized.
The importance of string field theory was not just that the equations looked cleaner. It suggested that string interactions might be describable with the same mathematical rigor as the quantum field theories already used in particle physics. The framework behaved less like a loose collection of ideas and more like a self-contained mathematical engine. But in theoretical physics, solving one problem often reveals an even bigger one. As string field theory made the mathematics more stable and organized, it also exposed a much deeper level of complexity hidden underneath. The compact equation was not the final answer. Instead, it became a gateway into an enormous mathematical landscape. From that single formulation emerged huge numbers of derived equations, hidden symmetries, and additional dimensions that naturally appeared inside the theory. What initially looked simple on the surface turned out to contain an almost endless depth of mathematical structure beneath it. This revealed something important about modern theoretical physics. Sometimes a theory becomes more mysterious precisely when it becomes more complete. And for supporters of string theory, that growing complexity was not necessarily a weakness. To them, it suggested that the universe itself might be far richer and more mathematically intricate than scientists had ever imagined before.
One of the strangest aspects of string theory is that it does not fit comfortably inside the universe we normally experience. In everyday life, we think of the universe as having 3 dimensions of space: length, width, and height, plus time. But according to string theory, that may not be enough. For the mathematics of the theory to remain internally consistent, space-time appears to require additional hidden dimensions. Some versions of the theory suggest a universe with 10 dimensions, while more advanced formulations propose 11. Most of these extra dimensions would be incredibly small and hidden from direct observation, which is why we do not notice them in ordinary life. This idea leads to an even more surprising possibility. Our universe may not be the only universe that exists. According to some interpretations of string theory, our cosmos could be just one bubble universe inside a much larger, higher dimensional reality. Other universes might exist alongside ours, each with different physical laws, particles, or even different numbers of dimensions. Together, this enormous collection of possible universes is called the multiverse. For many physicists, these ideas completely changed how they imagined reality itself.
String theory also connects to questions about the future of the universe. According to modern cosmology, our universe is not expected to last forever in its current form. If present theories are correct, the universe will continue expanding for unimaginable lengths of time until it eventually reaches a state called heat death. In that distant future, stars will burn out, usable energy will disappear, and physical processes will slowly come to an end. The universe would become cold, dark, and increasingly inactive. Some speculative ideas connected to string theory go even further. If higher dimensions and multiple universes truly exist, some theorists have imagined the possibility of moving between universes under extreme conditions. These ideas remain entirely theoretical and far beyond anything science can currently test, but they show how far modern theoretical physics is willing to explore when trying to understand the ultimate structure of reality. Michio Kaku often presents these concepts in an ambitious and visionary way.
He describes them as possibilities hidden within the mathematics of string theory itself. However, many physicists remain cautious. For critics like Richard Feynman, mathematical beauty alone is never enough. No matter how elegant a theory appears, science must eventually return to experiment, observation, and measurable evidence.
There is an uncomfortable question hidden inside the debate over string theory. The question is not simply whether string theory is correct or incorrect. The deeper question is this: what if rejecting it too early would have been a major mistake for physics? Richard Feynman believed strongly that science must stay connected to experiment. In his view, if a theory cannot be tested, then it risks drifting away from reality. But some physicists argue that if science becomes too strict too early, it may accidentally block important discoveries before technology has the chance to catch up. String theory is a good example of this problem. When the theory first appeared, it was still mathematically incomplete and far beyond experimental reach. It required decades of development before scientists could even begin imagining possible ways to test some of its predictions. If theoretical physicists had abandoned the idea immediately because experiments were impossible at the time, physics might have lost one of its most ambitious attempts to unify the laws of nature. This becomes especially important when studying the origin of the universe itself. According to general relativity, if we trace the universe backward in time, everything eventually collapses into a singularity, a point where density and curvature become infinite. At that point, the known laws of physics stop working properly.
The singularity problem reveals one of the biggest weaknesses in modern physics. Our current theories can describe much of the universe extremely well, but they struggle when dealing with the earliest moments of the cosmos. Physicists believe that a deeper framework may be required to understand what truly happened near the beginning of time. Supporters of string theory argue that it could potentially provide that missing framework. But there is also another possibility. What if string theory ultimately turns out to be wrong? In that case, generations of physicists may have spent decades exploring a mathematically elegant structure that never actually connects to physical reality. Its beauty would then represent not discovery, but a sophisticated illusion. And this is why the debate remains so important. Modern theoretical physics exists between two powerful philosophies. One side insists that science must remain grounded in direct observation and experiment. The other believes mathematics itself can sometimes guide scientists toward deeper truths long before experiments become possible. Neither side is completely sufficient on its own. Without experiments, physics can drift into speculation. But without bold mathematical exploration, science may never move beyond its current limits. And somewhere between those two approaches lies the future of theoretical physics. The story of Richard Feynman and Michio Kaku is often presented as a battle with a winner and a loser. But in reality, the debate was far more important than that. It revealed how scientific progress actually works. Physics does not advance because everyone agrees. It advances because strong ideas are challenged by other strong ideas. Throughout history, major breakthroughs in science have usually emerged from this kind of intellectual tension. In modern physics, two different instincts constantly compete with each other. The first pushes science toward bold new possibilities. It encourages physicists to explore mathematical ideas far beyond current experiments. The second instinct acts like a safeguard. It demands that theories remain connected to measurable reality. Both are necessary. Without imagination, physics becomes trapped inside old ideas and stops evolving. But without skepticism and experimental testing, theories can drift too far away from reality and become impossible to verify. That tension between creativity and evidence became one of the central themes in the debate over string theory. Modern theoretical physics still carries both legacies today. Physicists continue using Feynman's methods, such as Feynman diagrams, to calculate particle interactions with incredible precision. At the same time, researchers continue exploring advanced theories like string theory and quantum gravity in hopes of discovering a deeper description of reality. In many ways, physics now exists between two worlds, between what scientists can directly measure and what mathematics suggests might exist beyond current observation. Even after decades of progress, some of the biggest questions remain unanswered. Scientists can describe particles with extraordinary accuracy. They can model gravity across galaxies and black holes, but the ultimate structure of reality is still unknown. Are particles truly fundamental? Or are they actually tiny vibrating strings hidden beneath the surface of space-time? No one yet knows the answer. And that may be the real legacy of the debate between Feynman and Kaku. The lesson is not that one side was completely right and the other completely wrong. The real lesson is that science advances at the boundary between imagination and evidence. Physics moves forward when bold ideas are constantly tested against reality. And that balance remains one of the most powerful engines of discovery in human history.